Good morning all. Today we will see solving of MDP using policy iteration method. So MDP is a set of states, actions, transitions, rewards and the initial state. Here we are going to discuss solving MDP. So the objective of solving an MDP is we need to find the value function V R Q. So there are the various methods for solving MDP. The first type is which is linear programming. The second method which we have is a dynamic programming. In this dynamic programming, we can approximate the value function at faster rate. There are basically two methods in dynamic programming. One is the policy iteration and the second method is a value iteration. So whether we may be discussing about a policy iteration or value iteration, the main objective is we need to find out what is the value function, either it is V or Q. So as we said in the linear programming, it is a set of equations where we are going to maximize the rewards and find parameter, and it is very tedious process which is going to solve, which is a difficult process. Whereas dynamic programming, it will reduces the computation complexity and the solution we can find out at a faster rate compared to linear programming. So the solving of MDP will be takes place either through policy iteration or value iteration. Now first we will see the policy iteration, then we are going to discuss the value iteration. Yes, the policy iteration method. So this method, it is used for evaluating a policy and improves the policy until obtaining optimal policy. So in the evaluation of policy, we are going to compute the value function. So whatever the value function which we are getting, that will be used for improving the policy. So in the policy iteration, we have two steps. It is a two-step method. First, we are going to evaluate the policy, that is a policy evaluation. The second step is policy improvement. So first we will see the policy evaluation. We are going to start with an policy. Let us assume the policy is pi 1. Then we are going to evaluate the policy. So what is the evaluation of the policy means? It is to find the value function of the policy phi1. So the value function, we can take this one as v1. So first we will take a policy phi1. Then we are going to evaluate the policy for obtaining a value function v1. By using this value function, we go for improving the policy. Then we will obtain a new policy phi2. Again, we will take the policy evaluation for getting the new value function v2. Based upon v2, we go for policy improvement for getting the new policy which is phi3. So this process will be continued until we are going to obtain the optimal policy which is phi dash. So when the optimal policy is obtained, so for a optimal policy, the value function is also an optimal value function. This value function is unique for a particular policy phi. Once we attain the optimal value function v star, then we can't get a better policy than optimal policy, that is pi star. So for optimal policy, the theoretically we will consider Vt minus V of t minus 1 is equivalent to 0. What indicates? So for two consecutive time instants, one is current time t, the previous time t minus 1, whatever the value function which you are obtained at t minus at t1 minus 1 time the value function, the difference in this one is equivalent to 0. This is theoretically, but practically there will be a little bit a difference which we are going to take as the acceptable error, that we can write as the value function at a time t minus the value function at a t minus 1 time is we are going to evaluate until the difference is equivalent to a small error which is epsilon. So this we can consider as the stopping criteria. Policy evaluation, the value of a state S under a policy pi, we can express as v pi of S, that is the value function of state S for a policy pi is equivalent to summation of all the actions, the probability of taking an action in a particular state S multiply with S dash comma R, the probability of change of state to S dash with a reward of R from a state S with the action of A multiply with the reward current reward R plus a discount factor gamma and V pi of S dash. For a particular action, whatever the next state is there, that we will take as S dash. So the policy evaluation, it is an iterative method. As it is an iterative method, so for a particular policy pi, we are going to evaluate the policy by some approximate value, that is v0, v1, v2 like this until the optimal value function v star using Bellman equation. So for updation of the value function for k plus 1 iteration for a particular state S, we can write as the same as that of above equation. We can write as summation a pi of a for a given S, summation S dash comma R the probability of change of state to S dash with a reward of R when we are in state A with the action multiply with R plus gamma times of, this is the previous iteration. So what is the previous iteration? We can write Vk of S dash, where S dash is when we are in state S for a particular action A. So we are going to change to the new state that will take us B dash. Now we will see one example where we are going to be considered a policy pi, and we want to calculate the value function v pi for a particular function. For a particular policy pi, we want to calculate the value function v. So first we are going to initialize v naught for a particular policy pi. We will take all the state values as 0. So let us consider total we have 7 state. So this is corresponding to S1 state, S2 state, S3 state, S4, S5, S6, S7. So I am assuming my MDP is consist of that state space which is of 7 states, that is S1 to S7. So we are going to initialize a V naught for a particular policy pi with all zeros. So now let us assume we are in S0 state. If you take an action A1, we are going to reach the state is S1. If you take an action A2, we are going to reach a new state which is S2. Now if you take an action A3, we are going to change the state to S3. Let us assume the probability of taking action A1 in S0 state is 0.5. Taking an action A2, we will take this one as 0.3, and A3 taking the action in S0 state with a probability of 0.2. When we take action A1, the change of state is S1 with an return. Let us assume this is equivalent to 8. For S3, S2 state with action A2, let us assume the return is 12. For S3 state with the action of A3, we will take the reward is equivalent to 5. We will assume the probability of change of state with the reward from a particular state with the action we will take for simplicity it is equivalent to 1. Now our objective is we have to find out the V1 of pi dash. So V1 of pi dash is nothing but the value function we need to compute for S1 state, S2 state, S3 state, S4 state. Let us assume this I'll take as S0, S1, S2, S3, S4 and S5, S6. Here also I'll change from S1 to S6. Now in a given state S0, we are taking the action A1, A2, A3. So for computing S1 state for the value function for S0 state, we will evaluate like V1 of S with a policy pi is equivalent to sum of all the actions pi of A comma, the state is S0 we are considering, sum of S dash R, the probability of S dash from the state S0 with a particular action A multiply with reward R, discount factor gamma, V naught of S dash. So this is the value function which we are given. So for S0 state, we will write this expression as a v1 pi of s0 is equivalent to, now here we are taking total 3 actions. So that we can write as summation, right? As it is, we are taking 3 actions. So we are going to find out for action A1 as well as for action A2 for action A3. Now the probability of pi of A from S0 state, pi of A2 from S0 state, pi of A3 from S0 state, we are going to be multiply this one with S dash comma R. The probability of change of state, for simplicity we are consider as 1. So we will write this one as R plus gamma times of V naught. So when we take action A1, what is the change of state? Which is equivalent to S1. As it is a summation, you will write plus pi of A2 at S0 multiply with summation S dash comma R. Reward will take as R plus the discount factor as 1, a V naught of. So when you take action A2, the next state is equivalent to S2 plus summation S dash comma R plus gamma times of V naught of. When you take action A3, we are going to get the next state is equivalent to S3. That will write. Now we will substitute the values. So here we are interested to find out the value function V1 for a particular state S0 by substituting the value. So the probability of taking an action is 0.5 multiply with the reward. What is the reward we are having? 8 plus. So for simplicity, we will consider the gamma is equivalent to 1. 1 multiply with, as we are considered the V of S for initial, for each and every state, the value is equivalent to 0. So V naught of S1 is also going to be 0 plus, for taking an action A2 from S0 state, the probability is 0.3 multiply with the reward is 12 plus gamma value is 1, and the V naught of S2 is equal to 0. So substitute that value plus, for taking action A3, the probability is 0.2 multiply with the reward is 5 plus the discount factor gamma is equivalent to 1 multiply with a V of S3. So for S3, for V0, the previous value is equivalent to 0. Substituting this value, now we are going to get this value as 0.5 into 8 plus 0.3 into 12 plus 0.2 into 5, which we can write as 0.5 into 8 is equivalent to 4 plus 0.3 into 12, which is equivalent to 3.6 plus 0.2 into 5, which is going to be 1, which will give us as 4 plus 3.6, which is 7.6 plus 1, 8.6. Now this is the value function of V1 for S0 state. So when we are updating the V1 of S for S0 state, we will update with 8.6. Similarly, we are going to calculate for S1, S2, S3, S4, S5, S6 states. We are going to update this one. We will compute all the V1 values of S for every state. So repeat this process to find the various value function until what point we are going to be consider is for a particular iteration Vk1 of S minus Vk of S, if it is the difference in this one is less than or equivalent to the acceptable error, either you can take as epsilon or theta. Once we got this expression, once this condition is satisfied, at this point we will call the value function v pi as the optimal value function, and the policy at this instant we are going to be consider that one as the optimal policy pi dash. Now we will see the algorithm to evaluate a policy, that is iterative policy evaluation. So here we are going to discuss the algorithm to evaluate a policy. So evaluating a policy, it is also called as iterative policy evaluation for a value function v is equivalent to v pi. So here we are going to consider the input is equivalent to a policy pi, which can be an arbitrary or random policy pi you can take, which has to be evaluated. So this will consider as the policy to evaluate that we are taking as input. So let us consider the parameter where we are going to be consider the threshold value theta is very small and it is greater than 0. So this it is going to determine the accuracy of estimation. So we will initialize the value function v of s for all the states in the state space S except the terminal value function is equivalent to 0. That means the V of S we are going to be considered as 0, 0, 0 depending upon how many states we are going to have. So V of S will have the entries, it will depends upon how many states we are going to have. Now we go for looping. We will initial a difference we will take as delta is equivalent to 0. So what is this difference we can take as every iteration vk plus 1 of s minus vk of s. This is nothing but the delta function. Now we are going to loop for each and every state s where s is a member of the state space s. So the previous state value we are going to be allocate to the local variable small v for a particular state S, whatever the initial value is there, that is previous iteration, that we are going to be assigned to small v. Then we will update the new value function v of s with the Bellman equation, which is sum of all the actions, the probability of an action A in a particular state S multiply with a summation of S dash comma R, the probability of change of state to S dash with a reward of R from a state S with an action of A multiply with reward R, the discount factor gamma into V of S dash. Once we evaluate this V of S, we are going to find out the delta, where delta is equivalent to the maximum value of the previous delta and the change in v minus v of s. So whatever the maximum value we are having, that will be updated. So this process will be repeated until this delta is less than theta. So now here we are going to be loop this one, two loops we are having. One you can see the internal loop, the second one is the external loop. So the internal loop will be evaluated for each and every state. So this loop will be executed for each and every state, and each state if I have in each and every value function, if I have n number of state, we are going to be compute for S cross S times. Now this external loop will be iterated for one time. So the total time complexity here we are going to have as S square. Now we will see the implementation part. So implementation of the policy evaluation, that I'll write as PE. So implementation can be do in two ways. In the first method, by using two arrays, one array is for storing old values or old value function vk of s. The second array is which is to hold the new value function vk plus 1 of s. So this is called as out of place implementation. In the second method, we use only one array. The new value of v of s, the new value of v of s for a particular state overrides the old one. This is called as in-place implementation. So these are the methods we can use for implementation of policy evaluation. So once the policy evaluation is done, immediately we are going to improve the policy. So the second step in this policy iteration is policy improvement. Now we will see policy improvement. So after policy evaluation, we need to improve the policy. So for a particular policy pi, we are going to be calculate v pi 1. So we first initialize initially we will start with a particular policy pi 1. We are going to evaluate the value function for a policy pi 1. Then we are going to be find the policy improvement to obtain the new policy pi 2, such that the new policy, whatever the new policy which you are getting, it is always better than the old policy. Then only we can consider it as policy improvement. So how we can tell the policy is betterment is here, whatever the new policy obtained, it is always better than the old policy pi 1. So we have to construct the new policy in a greedy manner. Now we will see the steps to calculate new policy. So first step is we have to construct new policy. For every value that is V pi, and calculate Q pi. Here the value function V pi and Q pi are interchangeable. So the new policy we are going to get as, so the new policy is given as pi dash of S, which is equivalent to arg max of actions Q pi of S comma A. So the value function for a particular policy pi for a particular state S and action A. So for all the actions, whichever the maximum value function which are obtained, that action will be considered. So this we can write as by substituting the value function q of SA. So we can rewrite this expression as arg max of A, the expected value of, so q s comma A, that we can write as r of t plus 1 plus gamma times of v pi s of t plus 1, where st is equivalent to a particular state S. At time t, the action is equivalent to A, which we can rewrite as arg max of all the actions, summation of this expectation. If you write as summation, we can write as summation S dash comma R, the probability of change of state to S dash with a reward of R from a state S and action A, multiply with the reward, current reward R, plus a discount factor gamma, a V of S dash. So now let us consider, here we are in S0 state. When we will take action A1, we are going to the change state is S1. If you take action A2, the next state is S2. If you take action A3, the next state is equivalent to S3. Now, in this example, the new policy from a particular state, which is S dash, is given as the arg maximum of all the actions. What are the actions we are having here? It is A1, A2, A3, Q pi of S comma A, which is equivalent to arg max of. So what are the actions we are having here? So change of state is S1 with the action of A1 from the state S0. So that we can write as the arg max of Q of, for a particular policy pi, from S0 state. If you take an action A1, comma, the value function Q for a particular policy pi from state S0, action is A2, comma, the value function Q of pi from the state S0 if you take action A3. So out of all these quantities, we are going to take the maximum value of Qi for a particular function that will be picked. So let us consider, out of all this, assume this one is having maximum value. So what this one is signifies is, when we are in S0 state, always we are going to pick this action is A2, and we are moved to the next state is S2. So why we are considering here? Because we are assuming the value function in S0 state for action A2, which will have the maximum value. So this entire step we will call as policy improvement. As we are taking a particular action, so we are going to be pick, whenever we are in S0 state, as we are picking only S2 state, now this will become like a deterministic policy. Why it is deterministic policy means, when we are in S0 state, we are going to take action is only A2, and the change of state is S2 only always. So that's why this policy we can consider as a deterministic policy. So let pi and pi dash are deterministic policies such that state S, a member of the state set S for all the states, we are going to consider the value function q of pi, that is S comma pi dash of S is always greater than or equivalent to V pi of S. Then we can write the value function V pi dash of S is also greater than V pi of S. Therefore, the policy pi dash, either it may be same or better than the old policy. What is the old policy we are having here? Pi. So this we are going to be considered as policy improvement. Now we will see the algorithm for policy iteration. So what is policy iteration? So the policy iteration method is nothing but it is a two-step function which is a consist of both policy evaluation and policy improvement. So first we will carry out policy evaluation, then we go for policy improvement. So whatever the policy which you are get here, again we go for evaluating the policy evaluation, go for improvement. So this will be continued until we are going to obtain the optimal policy pi dash. Now we will see the algorithm for policy iteration. So in this policy iteration method, we are going to iterate over the policy evaluation and policy improvement until the convergence to optimal policy is obtained. So the objective of this one is we want to get the optimal policy. So we will start with a policy pi naught. We go for evaluating function for getting the value function v pi of 0. Then we go for improvement in the policy. Then we'll get the new policy which is equivalent to pi 1. Again, we will evaluate this policy for obtaining the new value function v pi 1. Then we go for improvement for getting the new policy pi 2. So this process will be continued until we are going to get optimal policy. Once we got optimal policy, if we evaluate this policy, whatever the value function which are getting, which is a optimal value function. So in the algorithm, first we go for initialization. We are going to write or initialize v of s with the zeros for s is belongs to state subspace, and we are going to take some input which is nothing but input policy pi which we want to evaluate. So second step is we go for policy evaluation. So in the policy evaluation, we are going to be loop. We will take the change, initial change in two successive iterations are equivalent to 0. Then we go for looping for each state S, which is a member of the state space S. We will update the value of v of s, that is old value, will assign to local variable v. Then we will obtain the new value function v of s, where v of s is given as summation of s dash comma r, p of s dash comma r for a particular state s with a policy that is phi of s, multiply with r plus gamma times of v of s dash. Now we will update the difference, that is delta is updated with the maximum value of a delta comma the new computed v of s. So this process will be done until the delta is less than or equivalent to some initialized parameter theta. So in the initialization, we also consider the accuracy parameter theta, which is equivalent to greater than 0, which is approximately you can take as 0, but a little bit greater than 0 we can have to consider. So this will be done the second step for policy evaluation. So in the step 1 we go for initialization, step 2 policy evaluation. Now we will see the step 3, which is policy improvement. So in the step 3 we are going to perform for policy improvement. So in this policy improvement, we will take a local variable which is equivalent to the policy state as true, which is a Boolean value. Now we go for each and every state S, a member of the state space S. We are going to assign the action which were considered to a local variable old action, which is phi of S. Then we will compute the new policy, that is phi of S, with argmax of all the actions, the value function q pi of s comma a. Otherwise, we also can write as a pi of s is the updation by substituting the value of q of sa as argmax of a summation s dash comma r p of s dash comma r for a particular state s comma a, multiply with r plus gamma times of v of s dash. So if the old action value is not equivalent to the pi of s, then we will make the policy stable, a policy state variable to false. So until the two consecutive policies are same, we are going to be iterate. So whenever the old action is not equivalent to the new policy, then we will make the policy state as false. So after some iteration, if old action is equivalent to the new policy pi of s, then we will make the policy state as true. So if the policy state is true, then we are going to stop the iteration and return the value function v, which is nothing but the optimal value function of v star, and we will return pi, that is policy, which is nothing but optimal policy pi star. Otherwise, if policy state is false, so that is else, go for step 2. So in the step 2, what we are doing, again policy evaluation, will come to policy improvement. So this is a iterative process until the policy state is equivalent to true. We are going to be change our execution from state 2, that is step 2 to step 3, the step 2 to step 2. So in the step 2, we are doing the policy evaluation. In the step 3, we are going to do the policy iteration. So once the two consecutive iterations, if old action is equivalent to new action, then you will get pi star. At that point, we are going to be stop the iteration. So this is the algorithm for policy iteration method, where it is a 3 steps. first we are doing initialization, and two loops we are having. One is policy evaluation, another one is policy improvement. This policy iteration, it will take a more number of iteration, and the time complexity for this one is equivalent to O of n3, where n is equivalent to the number of states. So the policy evaluation will be takes place for n square number of times, and policy iteration will be done once time, that is n. So as these are iterative method, we are going to get the time complexity is equivalent to n square into n, which is equivalent to n3. So this policy iteration method, it is very slow because more number of iterations we have to take place for getting the optimal policy. Next, we will see the generalized policy iteration, which is GPI. So in GPI, we will take a policy pi, take some evaluation function to set the value function v, then generate a better policy. So we are going to be iterate between evaluation of the policy, that is v, for a particular policy pi. From this, we are going to get a new value function v. From this, we are going to get the new policy, which is pi. So this is, we are going to get the new policy by applying a greedy method on value function v, which is for improvement in the policy. So for the new policy, again we are going to evaluate the pi. So this loop will be iterated until we are going to be attain the optimal policy. This value iteration, it is mainly focus on value function. In value iteration, only policy evaluation will be done. That is nothing but we are estimating what is the value function. So for a particular MDP, we have a particular V dash, that is optimal value of every state is fixed and it is unique. So in value iteration, we won't consider any policy. For every state, we will start learning the value function. So we are going to initialize the value function v with zeros depending upon how many states we are having. Now we go for calculating v1, v2, v3 for all the states until the optimal policy v star is obtained. So here we are applying some function when we are in initial value state as v naught. We will apply some function or method for policy. We don't have any policy. We are going to be apply some method for policy evaluation, that is f on v naught, which is going to give the new value v1, such that the v star of, that is value function, if you assume as v star minus v1, this absolute difference is always less than or equivalent to v star minus v naught. So this you can consider as old value, this you can consider as new value. So whatever the new value which you are obtaining, it is always the difference in optimal value function minus new value function is always less than or equal to the difference in value function and initial value. For every two consecutive states, this equation is going to be valid. So for any iteration at any point, let us consider at k plus 1. In the k plus 1, we will write v star minus vk plus 1. The difference, if it is equivalent to 0, then we can consider the vk plus 1 is the optimal value function. because in k plus 1, if you get the optimal value function, then the difference between these two, it is going to be generated as 0. So at optimal value function, so whatever the policy exists, that will be optimal policy because V star is unique. So as the optimal value is unique, once we got the optimal value function, at that time, whatever the policy which is existing, this we are going to be considered as the optimal policy. So that is a pi of s is equivalent to arg max of all the actions summation s dash comma r p of the change of state is s dash with a reward of r from a state s with the action of a multiply with a reward r gamma times of v of s dash. So the policy improvement will be done only once. So once we are obtaining the v star, then only we are going to be evaluate this policy. So the Bellman optimal equation for the value function is given as a v of k plus 1 of s is equivalent to the maximum of actions, the expected value of r t plus 1 plus gamma times of a vk of s k plus 1. So where st is equivalent to the particular state s, action at t is equivalent to particular action a. So which is going to give as the maximum value of all the actions. So the expectations we will write as the summation s dash comma r, the probability of s dash comma r at a given state and action multiply with r plus gamma times of a vk of s dash. So from a particular state, which action provide the maximum, that will be considered as a generate the next step. So the value iteration is always faster than policy iteration, because here we have only one iteration we are going to calculate only for finding out the value function until the optimal value function is evaluated. Now we will see the algorithm for value iteration. So first we will assume the acceptable theta threshold is greater than 0, and we will initialize the value function for all the states as zeros depending upon how many states we have. For every state we will write a 0. So where s is belongs to the state space s, and for the terminal state the value function is always 0. Then we go for looping. First we will initialize the delta is equivalent to 0. Then we go for loop for each state S which is a member of the state space S. First the V of S we are going to be assigned to a local variable V. Then we are going to be update V of S with the maximum value of the actions summation S dash comma R. The probability of change of state is S dash with the reward of R from a state S comma A multiply with R plus gamma times of V of S dash. Then we are going to be update the delta where the delta is given as the maximum value of the previous delta minus the old evaluated the value of V minus the new computed V of S. So this will be iterated until the delta value is less than theta. So once this condition is satisfied, then we are going to get the output where the output is a a deterministic policy. Pi that we can consider the optimal policy pi star, such that the policy pi of s is equivalent to argmax of all the actions summation s dash comma r p of s dash comma r for a given state s comma a multiply with r plus gamma times of p of s dash. So this is the algorithm for value iteration. So for solving MDP, we have discussed the two methods. One is policy iteration. The second one is value iteration. In, so in this session, we have discussed the policy iteration method.